Hello. Today in this class I will give just an example for uh, how the time and energy uncertainty of the Heisenberg principle. In this class it's continuous to the introductory guidance to the quantum mechanics course, and it's lesson 5. For this example, that suppose we have an electron in the n equal 3 energy level of hydrogen remains there for around 60 nanoseconds before moving down to energy level n2. In this example, we need to determine two values: a, the uncertainty in the energy released by electron in the transition, and b, determine the fraction of energy that this uncertainty represented with respect to the total energy released by the transition of electron, i.e., which is meaning that we are looking for the fraction of the stored energy in the emitted photon from the uncertainty of the total energy. So in this example, this is the figure that if we have an electron placed in higher energy orbit and it goes down to lower energy orbits, there is amount of the energy difference from the higher to the lower will be emitted as light or photon, and this photon will be carrying this energy difference. So there is kind of uncertainty, as we have learned from Heisenberg equation and the principle, that there is uncertainty in that energy released from the electron to be stored into the photon. So we have to calculate this value upon using the Heisenberg principle. This is the uncertainty in the velocity or the position, and this is the uncertainty in the momentum. It has to be larger or equal than, equal or larger than the h prime, which is a constant value. So in the same way, we have defined to calculate the energy from the Heisenberg principle, and we have delta t that is defined to be 60 nanosecond, and h prime, which is the same value there, but it's dot or prime is the same value in my class. Delta E equal h prime divided by delta t, and this is the constant value divided by 60 nanosecond, which is 10 to minus 9 second, and it will be resulted this is 1.75 10 to minus 27 joule. So this is simply how we calculated the uncertainty in the energy released by electron to the photon from this transition process. Now, to determine the fraction of that energy transferred with respect to the total energy released by the transition of the electron, this fraction can be calculated by applying the Rydberg equation. Rydberg equation, it's 1 over lambda, which is the wavelength of light emitted, and RH, this is the Rydberg constant, and it is 109,678 1 over centimeter. So this usually we convert to meter in our question, and 1 divided by n1 square minus n1 over n2 square. This is the indication for the atomic level, where from and into the electron would goes. So this is starting point. Usually it has to be higher than the initial or lower state level. And this can be used to calculate all spectral lines of hydrogen, and the values of n correspond to the allowed energy levels to atoms. So 1 over lambda, this is in the same equation, equal Rydberg constant multiplied by 1 divided by n1 square minus 1 over n2 square. It was moving from level 3 into level 1. So this is 1 over 2 square minus 1 over 3 square, 1 over 4 minus 1 over 9, and this is the constant value change from centimeter to meter, then we will get this is 1 over lambda as this value, while inverse of this value 1 over this value will get the lambda to be 6.56 10 to minus 7 meter. Now the energy of the photon, this is as a known equation, Planck constant multiplied by speed of light divided by lambda. So this is a constant value multiplied by speed of light divided by the lambda, which is we just calculated in the above equation. So we can get the energy will be stored or transferred from the electron to that photon. Then the fraction in the energy will be the total energy divided by this energy transfer to the photon. Then we will get that 5.8 10 to minus 9, the fraction of the energy. So this could be changed into the percentage, etc., as you like. And just to briefly show, this is the value that we have calculated in the previous section from this example, and it was described as the uncertainty in the energy released by the electron in the transition. And for today's class, thank you.